Mind the Gap, Secure File Sharing. This talk will be presented by David Balbás and Nicola Dardanis. Welcome.
All right, thank you. Good morning, everyone. We're Nicola, David. We're going to talk about secure file sharing. So we just saw this in the previous talk. Cloud storage is difficult and a bit broken when it's deployed out there. So today we're going to talk about an aspect of cloud storage which is kind of tricky. And as we saw in the slide of the athletics, all these providers were tripping in the file sharing part. So we're going to talk about file sharing and in particular about secure share folders. A secure share folder is simply a system where there is a group of users that upload files and retrieve them later, and all of these should be end-to-end encrypted. So there are many ways to build a folder like this. There's not a unique solution. There's one which is simply, I have a file, I want to upload it, I share it pairwise with everyone, or maybe I share the encryption keys, and that's it. It works, but it creates a few problems, and it's also not too efficient. So the attempts in practice, for example, the thing that Mega is doing is actually having a static folder key that all the members of the folder know, and they agree on it, and then they use it for encrypting the files or for deriving some file keys that will be used to encrypt these files later. However, this presents a few complications. The first one is that if we have a static key and we have some dynamic members, so this is that we have a sequence of epochs where the members of the folder change. This is not good because if I get removed from a folder, I shouldn't continue having access to the files that are uploaded, right? So we need at least some form of key rotation. And the second part, also related to the key rotation, is that this kind of system with a static folder key doesn't provide any security against state exposure. And if we're using this system, well, in general, no, but especially for sensitive data, we may want some resilience against a user having their state exposed. So what we tackle in this work is to build secure share folders based on this approach of group key agreement. And we're aiming for some protocol that has strong security, but is also efficient, and especially that is usable in the real world. So let's see how we do all of this. The first thing I want to talk about is security, and it's more about what is the security notion that we can aim for. So let's see this sequence of epochs keys, K0 all the way to somewhere in the future. These represent group changes or key updates that the members of a folder do. And let's assume that Alice and Bob are at epoch 0 in the folder, then Charlie joins at epoch 1, and then Charlie leaves the folder at epoch 5. So the keys that Charlie should have access to are clearly those in the interval 1 to 5, right? Those are the intervals that should be known, the keys that should be known by Charlie. And this notion of security is simply called, we call it interval security. Now, if there is a state compromise, if Charlie is compromised at epoch 3, what keys can we secure here in the persistent data setting? So as opposed to, for example, messaging where we can get rid of keys immediately, here Charlie must have access to these files persistently or to whatever is encrypting with these keys. So by correctness, we can't avoid the leakage of K1 and K2 because those keys have to be kept in memory. But we can prevent, if we want to, the leakage of future keys that the folder members are using. So this gives us a notion of post-compromise security that is possible to achieve in this setting. Now, how can we do this? Well, there is kind of naive, natural attempt to build this protocol, which is not bad at all. We can leverage a group key agreement like CGK, for example, the one that is used in MLS, where simply the members of the folder run a group key agreement. This group key agreement supports dynamic membership, so we get these epochs and security for like interval security for free. We derive a fresh key per epoch. This corresponds to members being added, members being removed, or simply members of the folder wanting to update their keys at some point to achieve post-compromise security. And we store all these keys. And then we access them when needed. This is nice because of security. TGK is good for this. We also have an MLS implementation available, so we should be able to use this and in the real world. But the problem here is that the state that the users have to keep is going to grow linearly with a number of epochs. And this has a few drawbacks related to storing this state, sharing it later, accessing it, and so on. So it's good to aim for a compact state as we do in the case of messaging as well. So we pose the question of whether we can get a good trade-off. And for this, we introduce Grappa. Grappa is a protocol that takes care exactly of this thing. It takes care of the key generation of a sequence of persistent keys and supports dynamic members. So how do we build Grappa? In a nutshell, we use two primitives. We do use a continuous group key agreement. We do use CGK as an MLS. And then we use a second primitive that we introduce in this work that we call interval scheme. So an interval scheme is essentially a compact primitive that allows a user to derive from a very small state, from a constant size state, a sequence of keys that are bounded to a given interval. From left to right, only those keys and nothing beyond. This gives us this interval security we were talking about. And this interval scheme supports updates. So these intervals can be extended, or they could, with the right implementation, even be punctured. How does this work together? I don't want to get into the details. This is a complicated protocol, but in a nutshell, CGK is used as a transport layer. We're using the CGK keys to encrypt the updates that are sent about the interval scheme. So the interval scheme keys are those that we're going to use to encrypt our files or to derive the file keys eventually, and CGK is only used to have a common communication channel for this purpose. So this is what we presented. We introduced Grappa, gives us strong security for persistent data. Of course, this is a probably secure protocol. We can prove that we get a good form of PCS and we get interval security. We have a compact state. We believe this is useful in practice. And also we find very interesting that is perhaps the first time, I don't know if anyone else has been trying to experiment a bit with this, but it's maybe the first time we're taking CGK to a use case which is not related to secure messaging, and we're studying how it behaves in practice. This is cool because everyone is going to have CGK in their phones, in their laptops soon. So it's kind of natural to see what else can we do with this protocol other than simply use it, well, not simply, but other than using it for secure messaging. So we want to look at the challenges that this supposes. And for this, we did a real-world implementation, or an implementation in the real-world setting that Nicola knows much more about it than me. So he will talk about that.
So thank you, David. So let's talk about implementation. We want to implement this secure share folder system on top of the primitive that David was talking about, Grappa. And yeah, as you can imagine, things don't work as easily in the reality. The main focus of this part of the talk are exactly those differences that we find between the model and the reality that we call engineering gaps. The first one, so in the model, users are described as letters and state are described as variables, but although this is very neat, in reality, this doesn't happen. We have real users with real needs and real devices that can have very different capabilities. For example, the type of crypto they can run. And another very well-known problem is that, or difference gap, is that the primitives are normally mathematical objects with mathematical properties and guarantees, but those needs to be respected in the implementation. And this requires that the execution platform provides us with some support for those operations. As well as implementers, we don't want to risk vulnerabilities and also to have to do more effort than necessary. So we want to rely on libraries. For example, in Grappa, David was talking about CGK, but in the implementation, we are going to use an MLS library. Now, to solve the problem of having the code running in multiple devices, and also to solve the need of the user to access the cloud application easily from multiple devices, we decided to go and try to implement it, the client for a browser. This comes with the fact that browsers implement the WebCrypt API, which is a standardized API and provides us with those low-level operation and cryptographic primitives that we need. And this is also implemented for other JS runtimes like Node.js and Dino. However, as this, again, in reality, this API is not as neat. For example, we found out that it exhibits no standard behavior in different implementation. This is due to some loose specification. For example, the MLS library that we use relies on the fact that public keys are calculated from elliptic curve, their encoded private keys when the public key field is missing. The excerpt that you see in the slide is for request for comment 5115. And you can see it states that the public key should be there, but it doesn't mandate it with a must. This leads to the fact that this works in Chrome, but Safari and Firefox will just crash when you try to import the raw bytes, while Node.js requires a workaround that we implemented. Next, the WebCrypt API has the problem that most of the new primitives are not there. It's quite old, and it's quite overprotective. Implementing actually advanced script is not easy. As a simple example, we want to do a key derivation from an HKDF key into another HKDF key. This doesn't work. The workaround is to first derive an HMAC key, then export it back into raw bytes, importing back into HKDF key object. This breaks the API abstraction, but there is no other way to do it. Next, engineering gaps. We are gonna shift the focus. So we are gonna talk about atomicity of operation in the protocols. As you have seen already in David's part, Grappa is made up of two main primitives, CGKA and an interval scheme. And however, the operation, each Grappa operation is atomic on the state. So either it completes the update or the state is completely discarded. This doesn't work really well in reality, especially when we want to consider resiliency against transient error like network failure or something like that. And we're gonna display why. But first, we talk about why MLS is indeed atomic as a primitive by itself. So in this picture, you can see a client that is in epoch 0 with a secret key 0. And the client wants to perform a commit operation. So it builds a commit message and sends this to the delivery service. Now there are two cases. In case of failure, the client can just discard the commit and stay in key 0, no problem. In case of success, the MLS client can process the commit and then advance to key 1. We want to stress here that the process of the commit happens afterwards the communication happened already with the delivery service. Now, okay. Now in Grappa instead, we want to compose MLS and interval scheme. As you already seen, we want to transport the interval scheme update through MLS. So to do this, we actually need to process the commit before add in order to have the new secret K1, so that when we encrypt the interval scheme update as an application message in MLS, we are sure that this is only readable by legitimate group members at the time. Then, however, if there is a failure, we are kind of stuck. We cannot roll back anymore to key 0 because the key 0 is already lost during the process of the commit. But there is no problem in case of a success. We still display this because you can see there is a no operation on MLS that is actually really stressing the fact that the update doesn't happen at once. The interval scheme process update is afterwards, right? So to fix this, what we do in practice is that we create the next K1 in memory. So we process in memory, and so we maintain in persistent storage key 0. At this point, we can encrypt the interval scheme, and upon success or failure, we can actually either roll back or complete the processing by overwriting on persistent storage. However, this practical use case have also maybe implication on security. So if we want actually to use MLS as a transport layer, our insight is that we need to study and formalize the security of this use case. And with this, we end the presentation, and we are open for questions. Thank you for listening.
I didn't quite understand the point made about sort of which keys are inevitably compromised in the case of a client being compromised, because yeah, if you can go back to that, thanks. So if you assume that a client is uncompromised up to a certain point, then it can delete old keys, delete old versions of documents, delete any documents that are deleted from the folder. So why is it inevitable that that information is
So
compromised?
you're talking about deleted files, if I get this right?
Well, so if you assume that the keys are necessarily compromised,
Mhm.
then that doesn't that prevent you from allowing the attacker to get the old versions of documents from the ciphertext?
So the thing is that we don't want to be re-encrypting the files in the
Okay.
folder, because this is an expensive operation that has to be done locally. So cloud providers are not very happy with this operation, and then the best you can do without re-encryption is something like this.
So it's a bandwidth and performance trade-off rather than
Yes.
an
yes,
inevitable
Yes. That's the
consequence.
idea.
Thanks.
Thank you for your question.
We'll take another quick question.
Maybe quick question. So syntactically, what you call interval scheme looks like a special case of something we call compact key storage.
Yeah,
Is is a formal connection, or is there something that interval scheme achieves which is more or less than CKS?
So we built this concurrently. We have a comparison to this. There are some differences, but maybe we can discuss this offline in detail, because it's an interesting question. Thank you.
Okay, let's thank our speakers again. Thank you.